try to look at tire example, so to say, and being able to understand that which car tire relationship is correct. And based on that, we need to understand that the correct setup is final domain model is strong aggregation composition fill diamond written as car. For example, car, where we have a diamond here, 0 to 4. Tire, meaning why strong? A part can only belong to one parent whole at a time. A physical tire cannot be bolted into two different cars simultaneously. It is completely locked to the identity of that one specific car while in use. Why 0 to 4 cardinality? Multiplicity must account for realistic life case status. Many to 0 tires represents a brand new car frame moving down the factory assembly line before the wheels are attached. 4 tires represent a standard operational car driving on the street. So we say this 0 tires represents a brand new car frame moving down the factory assembly line before the wheels are attached. This tires represent a standard operational car driving on the street, just like we mentioned. So many people assume it is weak aggregation because if you junk a car, you can save the tires and put them in a new vehicle. However, usable composition does not mean the parts are permanently glued forever. It means structural exclusivity because a tire cannot be shared by multiple cars. At the same moment, it is modeled as strong composition. This is what we need to understand. That car is a strong composition for a tire. And this is how we will model it. Now we need to understand that the 5 UML class relationship and their verbs. The first is generalization is a inherits solid line with a hollow triangle like this. A checking account is a general bank account. Implementation behaves as fulfills. Dash line with a hollow triangle. The printer software behaves as a standard hardware interface. For example, then we have association. Association has a, and it interacts. Solid straight line can have an open arrow like this. A customer has a physical debit card, holds a debit card, or a weak aggregation is part of loose. It is a solid line with a hollow diamond, unfulfilled diamond. A part of cash vault is part of an ATM kiosk but can't be removed. It's weak aggregation. Strong aggregation is consist of owns. It is showed with a filled black diamond. It is filled the same diamond but is now filled. An ATM consists of a built-in screen monitor cannot be displaced. So ATM is strongly aggregated with screen. So on the side of screen, this is a strong, if we remove this, then we can, the ATM can still exist. But if we remove this, this cannot exist independently without the ATM. Now we need to understand that typical errors to spot. We know that accidental underlying a regular class name or a standard attribute by accident. For example, drawing a box labeled U, bank account U. In UML, underlying strict means a static class or a specific object, example, a unique physical ATM instance. It breaks the diagram if you just meant a normal class blueprint. Invalid naming and symbols, using plural names, spaces, or specialized technical code symbols in class names. Naming a class, for example, ATM underscore machine underscore screen version 2, or customer, the name of a customer. Classes must always be singular nouns, capitalized, and clean of awkward, weird centers and symbols, just using like ATM screen or weird stuff. Invalid naming is not possible. And backward arrowheads, pointing inheritance or relationship arrows in the wrong direction. So drawing a hollow rectangle pointing from a customer to a premium customer. Generalization must always point from the specialized child back to the parent. So premium customer goes to customer. Backward arrow completely reverse the business logic. So now we have invalid composition number, writing a cardinality number other than 1 or 0 to 1 on the strong composition diamond end. For example, by definition, a strong composition part can only belong to one parent whole at a time. Putting many or two on a diamond side means a single tire could simultaneously belong to multiple cars, which is logically impossible. For example, if we say that this happens, this is a car, and if we put many here, so putting a asterisk or a 2 on the diamond side, or even 2, it can only be 1. So it's a strong aggregation, it's a strong relationship. It cannot be many. If a car has many, it means that a single tire could simultaneously belong to many cars, which is just not possible. Then we need to understand that why we need to think about architecture. Expensive or difficult. So architectural decisions are expensive and difficult to change once programmers have already started writing. Without thinking about architecture, you start writing code and later the bank decides that they must handle 50,000 users at the same exact second because you didn't plan the architecture. You didn't took care of which technology to use to make that happen. The system crashes under pressure and now you have discarded the code and rebuilt from scratch. And that's why we need to think about it. And if we define design versus architecture, we need to understand why IEEE concept we have here and architecture versus design breakdown in this context. So the decision to build the ATM network using a client-server architecture with a secure API gateway ensures the physical ATM never talks directly to the main bank database. Writing the exact class logic for the card reader, defining how the screen transition buttons look, and mapping out the include paths for login flow. This is part of the design. Architecture is the fundamental organization of a system. It defines core components, how they talk to each other than unshakable guidelines. These are the structural results. Design is both the active work of figuring out detailed specification, writing the exact class logic of the card reader, defining how the screen transition buttons look, and mapping out the include paths for logic flow. This is the design part. And again, in architecture, the decision to build the ATM network using a certain client-server architecture or secure API, ensuring the physical never talks to the main database. This is architecture-related technologies. Then we need to understand that what a component is. A component is an independent, modular, easily replaceable part of the system where it can be built, updated, and tested entirely on its own. It's independent. So the recipient printer coupon runs its own isolated internal code logic to feed paper and burn ink. And the property of a concept is that well-defined interface, it hides its inner mechanics and only exposes simple connection points. For example, the printer component exposes a clean interface. The ATM brain doesn't care how the printer works, it just hands over the text. So think of a component exactly like a plug-and-play USB hard drive device, like a mouse or keyboard. You can unplug broken keyboard and plug it in a completely different brand. As long as it has a standard USB connector, the interface, it works instantly without you needing to redesign the computer's motherboard. Based on that, it's replaceable. You can swap it out completely without breaking the rest of the software. If the bank switches from physical paper to receipts to digital e-receipts, the developer pull out the physical printer component and plug in the email sender component using same interface. Now, what are the 4 design directions? 4 pathways are top down, breaking requirements down, bottom up, building up from pieces, up, outside in, steering in with the user interface, and inside out, standing at the underlying hardware. Meaning that top down is high level requirements. You start with big business goals and break them into smaller. You have a clear mindset. For example, allows you start with the main goal, allows cash withdrawals, then you break it down into sub-steps: read card, verify pin, dispense cash. Bottom up, low level components. You build or gather small reusable pieces first, then combine them. You write independent helper modules, encryption tool, a network connector, and a database logger, and then snitch them together to form the main application. You want to maximize and best use when you want to maximize code reuse or are building on top of existing software libraries. Outside in, the user interface UI, you start with what the user sees and works backward into the logic. You design the physical touch screens, button menus, and screen flows first. Once the customer experience feels right, you write the background code to make the buttons actually work. The user experience is the absolute highest priority for project success. This is when you focus on UX. And inside out, the core hardware data. You start with technical constraints or devices and build outward. And you start with the physical card reader hardware and cache vault sensors. You write the low level drivers to the the machinery first, then build the user menus on top of them. You use them in case the system is heavily constrained by specific hardware capabilities or strict database structures. Now, what makes a software architecture good and how do we get there? Architecture is good if it satisfies all functional needs and quality goals, and you achieve this by applying proven principles and patterns to structure how parts talk to each other. Meaning that it's good if every functional requirements while simultaneously hitting all non-functional requirements, quality goals. You achieve this by successfully applying proven design principles and architectural patterns rather than just guessing from scratch. So functional fulfillment. So the system flawlessly executes the tasks the business requested. A user inserts their card, enters PIN, and successfully walks away with the physical currency. This is functional fulfillment. Quality goals. The system is stable, secure, fast, and easy for developers to modify. And these are non-functional requirements like transactions are fully encrypted, maintainability is properly done, etc. How do you get there? Of course, you get there, you apply structural rules like low coupling, keeping components independent, and high cohesion, ensuring each component does exactly one job well. For instance, the ATM cash counting module shouldn't contain code for rendering UI graphics. So if you have ATM cash counter, that has nothing to do with having the code for rendering UI graphics. This is a different component. And you choose an established battle-tested structural pattern to organize your software layers. You select layer structure, organizes code into strict horizontal tiers where upper layers you can only call the layer directly beneath them. So if there's a physical layer, for example, and if this physical layer displays the touch button, which calls the business logic layer, processes transaction, business logic layer, and then there's a data layer that connects securely to the bank database. This way, the physical layer touches the screen button, then it goes to process, transaction, business, then it goes to data, connects banks to the database, and this is how we functionally divide it into different sectors. And there are design principles, and there are architectural patterns. These are two different things. In design principles, you have low coupling, just like I mentioned, keeping the components independent on their own and not making them dependent. And high cohesion, ensuring each component does exactly one job well. So it does it one job well. Now, we look at what is the central message about architecture and quality. The fundamental message is that the structural choices made early in architecture completely dictates how well a system will perform, how well will it scale and stay long-term secure. So we look at it as a quality reality ATM example, building a cruise ship, for example. So now, first of all, quality attribute is security. It determines how early architecture dictates. It determines by how components are split across networks. So if the architecture allows the physical ATM terminal to directly execute raw SQL queries on the central bank database, a hacker compromises one physical ATM can steal the entire bank's data. Security must be built into structural topology using isolated API gateway. This is security attribute. This is how we deal with it, right? So we might say that the architecture versus quality reality, meaning that quality is not an afterthought. It is a direct product of the structure. So the fundamental architecture choices made early in a project completely dictates luck in how well a system will perform. You cannot fix a broken architecture by writing better code afterwards. You need to decide it in the beginning. Scalability and performance determines how well data flows through the system. If the architecture funnels every single ATM transaction request through a single central server bottleneck, the entire nationwide network will slow down or crash on payday Fridays, and a distributed microservices architecture handles this very well. Maintainability determines by how tightly bound the pieces are. If the business logic is tightly tangled with specific cash dispenser hardware drivers, upgrading to a new mechanical bill dispenser model requires rewiring the entire banking application from scratch. So what we understand from this is that you can easily rewrite a messy function or fix a bug in a day, but if you make a mistake with your system core architectural structures, fixing it later requires completely tearing down the application and rebuilding it from the ground up, costing the business immense time and money. Now we need to understand that is there any perfect architecture? No, because different quality goals naturally conflict with each other, meaning you must pick your top priorities rather than trying to achieve everything perfectly. Architecture is a game of compromise because different quality goals naturally conflict with one another. A system cannot be infinitely secure, blindly fast, completely fixable, and incredibly cheap all at once. You must explicitly prioritize what matters to your business the most. So, for example, security versus performance may be to keep data safe, ATM encrypts a withdrawal request with very secure route. It has 2 firewalls. This is at 3-year, but it adds a 3-second delay for the user waiting time. So there is always a byproduct. Now explain the security versus usability trade-off. For example, max usability, 0 friction. So the good is incredibly fast. The user walks up, taps the card, gets the cash immediately. But the bad is that there's zero security. If someone steals the debit card, they can drain the entire bank account in seconds. The real world user interaction, I love how fast this ATM is, but someone stole my wallet and took all my money. With maximum security, it's virtually unhackable. The ATM requires a 6-pin fingerprint mobile, but it's incredibly frustrating because simple cash withdrawal takes 3 minutes of stressful button. And this is too much, right? Now we understand that reliability and maintainability are trade-offs. Now, simple system, no redundancy, one primary application talks directly to the main database. The reliability impact is very low. If the server hardware fails or a bug crashes the software, the entire nationwide ATM network goes offline completely. The maintainability impact is very high. Extremely easy to maintain. When developers want to ship an update, they deploy code exactly one place. There is no sync bugs to worry about. But in case of redundant system, there's high reliability. 3 identical servers run simultaneously, continuously replicating data across geographical zones with the automated load balancer. Then the reliability impact is high because if a server A catches fire, the load balancer instantly routes traffic to B within milliseconds. It's very reliable. The user at the ATM noticed absolutely 0 time. Now, the problem is that the maintainability, it's very hard to maintain because maintainability becomes a nightmare. Code deployment must be carefully staged. Rolling updates data can become out of sync across databases, one server on the other, and the becoming distributed risk condition takes days of engineering. So the core is that redundancy breeds complexity. Complexity is the natural enemy of maintainability. When you prioritize reliability through duplication, you introduce massive friction. If a user withdraws 50 euros from ATM, that balance deduction must be instantly broadcast and locked across all backup servers. Managing this real-time sync without corrupting data requires complex distribution. So the rule of the thumb is that if your system absolutely cannot afford a single minute of downtime like an ATM network or a medical life support, you must accept the high cost and friction of a complex, hard to maintain redundant architecture. If occasional overnight downtime is acceptable, like a local school grading portal, keep the architecture simple to maximize long-term maintainability. Now we get to the question that how does architecture relate to complexity? We need to understand that there is a link, of course, between architecture and complexity. So architecture directly controls system complexity. Keeping a system simple and highly organized cuts down the software bugs and lowers the overall development cost. That's pretty much obvious, right? But we need to understand that architecture is a system primary defense against accidental complexities. This creates a tangled mess known as spaghetti code, or a big ball of mud. If module A talks directly to module B, which updates module C, which triggers an alert in module A, a developer cannot change a single line of code without accidentally breaking three of other features across applications. So a good architecture reorganizes these chaos into distinct isolated layers. Coupling, for example. So the first is coupling, which means that a high coupling, every piece of code is tightly glued to every other piece. High coupling. Uncontrolled complexity, no architecture. This is high coupling, which is not good because it's uncontrolled complexity. There's no architecture here. Controlled complexity, good architecture. So there's low coupling. Components are independent modules, so they are independent, that interact via strict minimal interfaces. They interact towards each other with strict minimal interfaces. Then we have cohesion. Low cohesion, as a single file handles UI rendering, user authentication, database writes, and hardware calls. Then we have high cohesion. Every class or component does one single job exponentially well. It's not that this is supposed to do everything. That's wrong. So we have high cohesion and low coupling. Coupling is like, coupling, dependent. This dependency is not good. So we need to have low coupling, that everything is independent on its own, and high cohesion, that every class is doing something of its own exceptionally well, 10 out of 10, rather than doing 5 different jobs and failing at all of them. Then we have bug tracing. Finding the most cause of a system failure requires hours of reading chaotic execution paths. But bugs are isolated instantly to a single predictable component layer. So we know that they are predictable to a single component layer. If we used low cohesion and high coupling instead, which is a bad practice. So high coupling being coupled, so coupled to each other, dependent on each other, and low cohesion let everything do everything, like let this do everything. If we did low cohesion, then finding the root of the problem would basically take hours. But then in high cohesion and low coupling, so high cohesion is that high cohesion is high responsibility for each thing. It just basically means so easy for us to find problems. The real world cost is that the no architecture curve is the first few months of startup is lightning fast because engineers just write code without thinking. However, as complexity builds up exponentially, adding a new feature takes longer and eventually engineers spend 90% of their time fixing regression bugs caused by tangible spaghetti code, causing development velocity to drop to bad. And a good architecture curve builds clear boundaries. For example, just like we mentioned, it creates high cohesion and low coupling, creating very good architecture. Then what are the coupling and cohesion? The concert hall analogy. So you want your modules to have low coupling, keeping connection between modules small and simple, and high cohesion. Keep all elements inside a single module tightly focused on one job. That is exactly what we talked about. Look at musicians at state. Every person is completely focused on highly specific job, playing the symphony. The violinist isn't trying to sell tickets. So this is high cohesion. And low cohesion is, imagine you mixed musicians, security guards, and ticket collectors and audience members all into one stage. So nobody knows what their job is. And for example, coupling is like, low coupling is like the orchestra and the kitchen staff. The orchestra is playing music on stage, and a separate catering team is preparing food in the kitchen for intermission. The only connection interface between them is simple schedule. Food must be ready at a certain time. The chef can change the soup recipe entirely without the violinist needing to retune their instrument. They are safely independent, so they are independent. Low coupling creates high independence. High coupling creates high dependencies. Imagine if violin's strings were physically tied to chef's soup or the chef's mood. If the chef is not there, then there's no violinist. This is so bad. Now when we look at core complexity reducing principles. So the main rules are: separate different scenarios, do not repeat your code, dry, keep interface stable, keep things simple, KISS, and hide non-essential details via abstraction. Now the core philosophy is that separation of concern. Split a program into distinct sections where each section addresses a completely separate business feature or logic, keeping the user interface rendering code completely isolated from database connection logic. This is what it does. What it avoids is massive tangible files that try to manage everything simultaneously. So this is separation of concern, keeping things separate. Separation of concerns. Dry. Don't repeat yourself. Every piece of system knowledge or logic must have a single, unambiguous, and authoritative within the purpose. Copy-pasting fragments across different classes, which create maintenance nightmares when a business rule changes. So moving a common currency formatting calculator into a single usable helper function instead of rewriting it inside every single unit account report. Then interface stability, that design external facing connection points of a module to remain permanent and unchanging even if the internal hidden code is completely rewritten. Meaning that a central banking API gateway keeps its verify pin parameter format exactly the same, allowing internal validation security patches to deploy without breaking physical ATM machines. Then we have KISS, keep it simple and stupid, which means that systems work best if they're kept simple rather than made complex. Simplicity should be a key goal in design, and unnecessary cleverness should be avoided. Over-engineering systems with features and all of this stuff is not right. Writing a straightforward readable if-else block to validate a user instead of building a highly complex multi-tiered dynamic permission evaluation engine for a simple application. It's crazy. Being able to create abstraction via information hiding, expose only the essential high-level functional details of a component to the outside world while completely hiding non-essential complex inner mechanics. A programmer calls a high-level function like card reader without needing to manage physical hardware voltage signals, USB drivers, ports, or sector memory bufferings, forcing programmers to understand low-level infrastructure just to execute a basic command. So we are using abstraction via information hiding. We expose only essential high-level functional details of a component to the outside world while completely hiding the non-essential complex inner mechanics. A programmer, for example, calls a high-level function whatever it's doing without need to manage physical hardware voltage signals or USB driver ports or sector memory buffers, I don't know. But this forces developers to understand low-level architecture. Now, after that, we understand what is a hierarchical structure, and it's 3 types. It is an organizational schema that ranks eliminates to reduce complexity. The three types are whole parts aggregation, stacked operational zone layers, and parent-child inheritance trees. So a hierarchy is organization scheme that ranks and groups system elements into a clear vertical levels to reduce complexity instead of each component interacting with everything else in a chaotic network, organized into specialized tiers. Now, what we understand from here is that the whole part assemblies, aggregation, composition, what happens is that elements are physically or logically nested inside a parent container. The parent is the whole and the lower parts are the parts. An ATM sits at the top, containing a card reader, a cash dispenser, and a receipt printer beneath. Encapsulation: small groups, highly cohesive units together so they can be managed as a single entity. Then we have stacked operational zones, layering. We know that elements are organized into horizontal stacks, tiers. Upper layers are consumers that can only call the services of the layers directly beneath them. So they can only call what's beneath. UI can only call business logic can only call database layer, SQL layer. And this way, we understand that separation of concerns, different types of technical logic, so changes in one layer does not break the entire system. Then we know parent-child trees, inheritance and generalization. Specialized children elements inherit properties, attributes, and behaviors from a general abstract parent element at the top, which means it's a dry, do not repeat yourself. Eliminates redundant code by sharing common behavior across multiple classes. So a bank account class branching down beneath it are specialized child classes, checking account, savings account. And we know why we did it. Then we need to describe general 5-layer architecture for web applications. We know that the top layer is UI layer. Then we have, it's the HTML, CSS, it's managing the user interface layer. Then we have the security layer, this is the second layer. It makes sure that everything is secure. Then we have the business layer. Then we have the technical service infrastructure layer, which makes sure that the third-party integration and plumbing services are supportive. Reusable modules are sent automated notification emails, handle file compression, or connect external SMS gateways. Then we have on the bottom data access, which is directly communicating with physical databases, managing storage schemas, and running data queries. This is like separation matters in web like a busy restaurant. So first you print the menu, then the host checks before you letting the customers inside, then the chef decides who to prepare the dish for. So these are different layers. Because these distinction layers, restaurant can hire a new interior designer to completely overhaul dining room without needing to retain the chef, meaning the business logic. So one can be worked on. If somebody fires or quits, he can still work on it. A new guy can work on it. And what are the rules of a strict layered architecture? We know that a component can only interact with elements inside its own layer or directly invoke the single layer immediately beneath it. It can only work on its own or underneath. That's it. It cannot go all the way here and start working there. So why is it enforced? First of all, no upward call. Lower layers are completely blind to the layers above them. A database layer can never initiate a call to a user interface layer. Why is it enforced? It prevents circular dependencies that make code impossible to test or reuse independently. No skipping layer, meaning that layer n can only talk to layer n-1. It is completely forbidden for layer 1 to bypass layer 2 and call layer 3 directly. If layer 1 bypasses layer 2 and layer 2 loses its role as a protective gate, the system becomes tightly coupled. It's a strict layer. It's allowed for layer 1 to access layer 2. But layer 5 cannot access anything. It's isolated. So it can access only something that's beneath it and access itself.